All right, well, it's Friday. Happy Friday, everybody. You guys got through your first full week of classes, and I hope everything's going well so far. I mean, during the first week, generally, things are pretty good, but, you know, that might not be the case with everybody, but I hope that is the case. How are we feeling about everything so far? All right, great. Thumbs up. Happy to see that. Okay, I'm supposed to remind you, if you have not done your daily symptom monitoring thing, please do your daily symptom monitoring thing that the university wants us to make sure you guys do that each day. Okay. Just a little bit of clarification once again. Or I guess maybe a reminder, because I think I pointed this out, is that the likelihood function is not the same thing as a beta probability distribution. They are of the same form, okay? They have the same shape, but they are not the same, okay? In that, you know, when you find the binomial probability for some set of data, okay, with n observations and z successes, this is what you have, okay? And you would find this in R using D binom, right? You would do D binom, z successes, n trials, theta as your probability. But again, when we are talking about a likelihood, what's happening there is that the data is treated as fixed and theta is a variable. Theta could go anywhere from 0 to 1. Whereas when we're talking about a binomial probability calculation or a binomial distribution, that's actually a probability mass function, right? It takes on only whole numbers, and you say every possible value from 0 up to n, and those things would add up to 1. And then if we're talking about a beta distribution, the beta distribution will integrate to 1. Okay? But the likelihood function of some set data, n observations, z successes, is proportional, but is not equal to a beta distribution with shape parameters alpha equal to z plus 1 and the beta shape parameter equal to n minus z plus 1. Likelihood functions don't integrate to 1, whereas a beta distribution will. The beta distribution has that constant up front. And in Wednesday's lecture, when I created those plots, we had the prior, the likelihood, and the posterior, that likelihood again was multiplied by some kind of constant to kind of inflate it. So it's kind of on a similar scale as the other values. But again, if you actually plotted the actual likelihood, it would end up being very flat. And we had an example of that on Wednesday, but I just want to kind of remind you that's what's happening. And so when you do the homework, and I ask you to kind of plot the likelihood functions, when you kind of combine them, you're going to end up probably using the beta distribution function to plot these things, but that's not the likelihood. Okay, it's separated by a factor there, constant. All right, so in today's lecture, we are going to take a look at basic Bayesian inference. Just kind of the idea that once we've guessed kind of some parameters, or we figured out the posterior distribution, how can we do some inference? How can we answer questions about, you know, things related to that? Okay, so we're still looking at the beta binomial model, and we said the beta distribution, which is a probability distribution that we use to describe a probability, right? A proportion, some value between 0 and 1. So that beta distribution is the conjugate prior when you have data that comes from a binomial situation, okay? A binomial or Bernoulli situation. So if the data has a binomial or Bernoulli likelihood, the beta distribution would be the conjugate prior for that unknown parameter. We say, okay, let's say our data comes from the binomial distribution. You have a total of n trials, and out of n trials, you have z successes. And we said, the probability of a success for each trial is theta, and therefore when you calculate this likelihood, ignoring any kind of constants, we just say, well, it's going to be proportional to theta raised to the z, theta being the probability of the success, and how many times does the success happen? It happens z times, whereas the number of failures we encounter is that probability is 1 minus theta. And how many times does that happen? Well, if you have a total of n trials, it happens n minus z times. Okay? So the beta distribution, which is our prior, has this PDF, okay? Theta raised to the alpha minus 1, 1 minus theta raised to the beta minus 1. And we do have to kind of arbitrarily select those parameters, alpha and beta. Hopefully, we can do it in such a way that's a little bit informed and not just total guesses, but at the end of the day, it is a little bit subjective. It is a little bit, it's not exactly a precise way to go about when you pick the prior distributions. And I know that makes a lot of you uncomfortable, okay? The fact that two people could end up picking different prior distributions, and if two people have different prior distributions, then the conclusion will be different, right? It could be different. And that's just the way life works, right? We go through life, and two people, based on their childhood experiences, could end up having different kind of ideas about the world. And they can look at an event, they can look at something, and they can walk away with different conclusions based on observing the same data. And so it is a little bit uncomfortable, but I think it also reflects a little bit of reality that people, based on your prior experience and your subjective beliefs, that might inform what parameters you use for the beta distribution. Now, when we have lots of data, the prior distribution plays a less role and the data plays a larger role. But if you only have a little bit of data, then you're going to rely more heavily on that prior distribution. All right, so anyway, when you combine the likelihood and the prior, and then you go through some calculations to figure out what the normalizing constant is at the very end of the day, you have the posterior distribution. This is the distribution. This tells us what we believe that mystery parameter theta is, okay? It's a random variable. It tells us what we believe theta to be if we've seen the data observed z, right? We've seen z successes in n trials. And the resulting distribution is basically we add the number of successes to that prior shaped parameter alpha. We add the number of failures, n minus z, to that prior shaped parameter beta. Because that prior distribution, we said alpha is kind of like the number of successes you've seen, and beta is kind of like the number of failures that you've seen. And we just take the data we've observed, which is basically, we saw this many more successes, this many more failures, we add those, and that becomes kind of our new beta distribution. And it's going to have this equation, theta raised to the z plus alpha minus 1, and 1 minus theta raised to the n minus z plus beta minus 1. So that's kind of a recap of what we've done on Monday and Wednesday, and I hope this slide feels okay with you guys. All right? If there's any questions, don't hesitate to ask. Let me go ahead and give you your first view quiz answer for today. First view quiz answer for today is B. B as in bear. B as in bear. Or beta, binomial. All of these B words. Okay, so we've got the beta distribution, and if we go on Wikipedia, right, and we said, let's look up the beta distribution. We hit beta distribution. We could go through all of these properties, and we say, okay, what is the mean of the beta distribution? If you have shape parameters alpha and beta, the mean is going to be alpha divided by alpha plus beta. Okay. I thought it'd be worthwhile to just at least explore or prove, derive that somehow. Okay, so let's go ahead and take a look. So when we calculate the expected value of the random variable theta, what we do is we take the integral across all possible values of theta. So it's the integral from 0 to 1, that's the support of theta times our PDF. The PDF being 1 over beta plus beta of alpha comma beta, theta to the alpha minus 1, 1 minus theta. Okay, so this is what we have. Well, this part, 1 over beta alpha beta here, the beta function, is a constant, so we can extract that. And now I have the integral of this. Okay? So here I've got theta times theta alpha minus 1. Right? And so this will combine to be theta of alpha plus 1 minus 1. Is that okay? Now, I could have just chosen alpha plus alpha, but the reason why I want to leave it in this form is because remember that identity where we said, the integral of this part is going to be equal to the beta function of alpha comma beta. Well, here I've got theta to the alpha plus 1. So this part will become beta function of alpha plus 1 comma beta. Is that all right? That this integral becomes this constant. I think we kind of talked a little bit about that, I think, on Wednesdays. Okay? So I have the beta function here, beta of alpha comma beta of alpha plus 1 comma beta. All right, so what is that? Okay, so again, this beta constant, this beta function, beta alpha comma beta, is gamma alpha gamma beta over gamma alpha plus beta. So I'm just using this definition of the beta function there. So this part becomes, it's 1 over beta. So we're going to have gamma alpha plus beta divided by gamma alpha gamma beta. This part is going to be gamma alpha plus 1, gamma beta, gamma alpha plus beta plus 1. All right. So I'm going to combine all of these things. And so this thing here, gamma alpha plus 1, right? Gamma x plus 1 is exactly equal to x factorial, right? So when you have, assuming we have integer values here, okay? But it also, okay, so we got gamma of x plus 1 is equal to x factorial. And this identity is also true whether or not x is a integer. Gamma of x plus 1 is going to be x times gamma of x, right? So if you think about what x factorial is x times x minus 1 factorial, okay? X minus 1 factorial is just gamma of x. So this is going to be x times the equivalent of x minus 1 factorial, or gamma x. So this part right here, gamma alpha plus 1, becomes alpha gamma alpha. I feel like I'm talking about like sororities and fraternities or something here. But so we've got gamma alpha plus beta, alpha gamma beta, and we can divide out. We've got gamma alpha cancels out gamma beta cancels gamma beta, and we've got gamma alpha plus beta. Oh, and I'm sorry, this part. Gamma alpha plus beta plus 1 becomes alpha plus beta times gamma alpha beta. So this cancels out that thing. And we're going to be left with alpha divided by alpha plus beta. Okay. That's how we get the mean, okay? What about the mode? Okay, so the mean, when we look at this beta distribution, right, when we get this, if this is our thing, the mean, let's take a look at this orange curve, okay? The mean is where it would be balanced, right? So this thing, if we balance this, it would be 2 over 7, I don't know what that is, 0.28. It would be something around here. This orange curve, if we had to balance it, would be somewhere around here. But where's the mode? The mode is the tallest point. That's the peak. Okay? So the peak is a little bit different from the mean, the mode. Okay, so what do we want to do to find the mode? Well, to find the mode, we're going to take the derivative of this function. We're going to take the derivative of this function. We're going to find where this derivative is equal to 0, and that's going to be our mode. Okay? So we take our PDF. So if we have shape parameters alpha and beta, our PDF is this. We're going to take the derivative of this with respect to theta. We're going to set it equal to 0 and solve for where that is. Okay. Do I want to work through this? I guess. Oh, I already did the work. I just have to read it, right? Okay. So the derivative. Okay, well, this is a constant, so we'll just pull that out to the front. Okay, theta to the alpha minus 1. We're just doing kind of product rules things here, right? So it's going to be the derivative of this thing times this thing. So we got alpha minus 1 times theta to the alpha minus 2 times this part, product rule. And then we do the second part, what's the derivative of this times this? Theta to the alpha minus 1 times beta minus 1 times 1 minus theta to the beta minus 2. There's a chain rule here, so we have this multiplied by a negative 1. All right, now we just have to kind of rearrange terms and combine terms. So what I can do is I can factor out, so I've got two terms separated by a plus sign, and I can factor out theta to the alpha minus 2, and I can also factor out 1 minus theta to the beta minus 2, okay? So if I factor this out of this side, I'm going to be left with alpha minus 1 and 1 minus theta. And if I factor this out of this over here, I'm going to be left with a theta, okay, a theta here, and I'm going to be and beta minus 1. Okay. And what we want to do is we want to solve for values of theta, so this thing equals 0. So we can see right away at theta equals 0, this will equal 0. At theta equal to 1, this equals 0, and that makes sense, right? We can see, okay, well, we're going to end up getting a 0, and we're going to get, yeah, okay. So that's fine. So, but let's take a look at this, just this part, and solve for where this thing is equal to 0. Okay, so we're going to just kind of throw away this stuff. We're going to solve for where this equals 0. We got alpha minus 1, 1 minus theta times beta minus 1. So we just kind of have to FOIL this out. We multiply everything out. We get alpha minus 1 minus alpha theta plus theta. This becomes theta times beta. This becomes a plus theta. I think I triple checked my work just to make sure my LaTeX, I typeset this correctly, but there's a possibility I made a typo somewhere along here. Okay, and then so, you know, we just kind of factor a theta out of all of these terms, we rearrange stuff, and eventually we're going to get alpha minus 1 over here divided by alpha plus beta minus 2. And that is where the mode is, that's where the peak is. So if we take a look at this example graph where alpha is 2 and beta is 5, the mode is going to be 2 minus 1, 1 divided by 2 plus 5 minus 2, which is 5. So 1 over 5 is 0.2, and indeed, that is where our mode is. Our mode is at 0.2 in this graph. So that's the mode of the beta distribution. All right, and so anyway, we've done this work here, and with Bayesian stats, after you get your posterior distribution, you can create a probability interval, okay? This would be the Bayesian equivalent or alternative to the confidence interval. And different from the confidence interval, where a confidence interval, you weren't allowed to say the probability that theta is between here and here is there's a 95% probability that theta is between here and here. That was incorrect from a frequentist perspective, because from a frequentist perspective, theta was treated as a fixed value where there was no probability, no uncertainty. But now, with the Bayesian perspective, this unknown parameter theta is a random variable. So it's subject to randomness, and it is correct now to say that there is a 95% probability that theta is between here and here. And it feels like it's just semantics, or it feels like, what changed? Why am I allowed to say probability now versus I wasn't there? And it just, we've switched our perspective and we said, hey, we're going to treat this thing as a random variable. And because we're treating it as a random variable, there's now probabilities associated with it. So there's a few methods we can use for figuring out the bounds of the interval. One is the equal tail credibility interval, and I think this one's probably the easiest for us to create. And then the other is the highest posterior density interval. That one's a lot harder to create, I guess. There's tools in R that will do it for us, so maybe to you it's not that much harder, but mathematically it's a little bit harder. But I think maybe visually it also makes a little bit more sense. So the equal tail credibility interval, basically, once you get your kind of resulting interval, you just find, okay, where's the spot, if we want a middle 95%, where's the spot where I've got 2.5% in this side of the tail, and where do I have 2.5% on this side of the tail? All right, so here we're just gonna, I'm making stuff up. We're gonna just pretend we have this posterior distribution. This has nothing to do with any of the examples we've done so far. I'm just making up a posterior distribution as an example, and we're gonna just say, let's say this is my posterior distribution. It's got these two parameters. What are the bounds of my interval? And this is basically what it looks like. So if this is your posterior distribution for what theta is, okay? Wait, what did I? Oh, okay, I'm sorry. This is not even a, I confused myself. Here, I'm just drawing a skew distribution. This is for gamma distribution, okay? And so this is not the beta, this is a completely different thing, but just to kind of show the difference between what a equal tail versus highest density interval looks like. This is what we have. So here, I just want 2.5% over here, and I want 2.5% over here. So the size of this size is 2.5%. I've got 2.5% over here, and this would be my 95% credibility or probability interval here. All right, I've got 95% in the middle, and these would be the bounds. And the bounds in this case would be 1.08 and 6.82. And if I shade in the area over here, I have 2.5%. If I shade in the area over here, I have 2.5%. Versus the highest density interval, this would find the kind of narrowest range where you have 95%. And this would be equivalent to kind of dipping the resulting probability density in a shallow tub of water, if this makes sense at all. And you're trying to find kind of the line where only, as far as the tails go, only a total of 5% gets shaded in, okay? And so here, this side is not equal in area to this side, okay? But the height here, this value right here, is equal to the height over here, okay? And the total area in the green and the purple is 5%. The total area in the center is 95%. And the key here is that this height and this height are equal. This is the highest density, okay? The highest density is between here and here, and that still covers 95%, okay? So compare the highest density interval versus the equal tail interval. We have 2.5% here and 2.5% here, and we can see, you know, this is a higher density than over here. What's the interval we're supposed to use? Okay, really it's up to you. Okay, the creation of calculating the highest density interval mathematically is a little bit tougher, but we've got a tool using library HD interval, I should say, and you can calculate the bounds of the highest density interval using the function HDI. You give it, in this case, what you want, we want the middle 95%, the credibility mass to be 95%. And here I'm specifying the parameters of the distribution. In this case, a gamma distribution with shape equal to shape and rate equal to rate. Now again, maybe you have a beta distribution, you get something different. So this is what I've written. I wrote, whether you select the equal-tailed interval or the highest posterior density interval, it's correct to say that there's a 95% probability that the unknown parameter falls within the bounds of the interval. This probability reflects our subjective belief about the random variable. We're treating this as a random variable. The credibility interval incorporates our prior knowledge in the prior distribution, which was used to calculate the posterior distribution. In the case where we have little observed data, the credibility interval that we end up getting, this posterior distribution, it's based on the posterior distribution, that's greatly influenced by our prior beliefs. If we have a lot of data available, then it will be influenced more by the data. Okay. A frequentist confidence interval, on the other hand, is determined only by the observed data, and intervals based on little data will have huge margins of error, and intervals based on more data will have smaller margins of error. And you've got some examples of that in your homework. I believe you have to do this, right? You create a traditional confidence interval using kind of the traditional way. When you have only a little bit of data, you end up getting these huge error bars, or this huge, very wide interval. And we know wide intervals just aren't very useful to us, versus the ones where you incorporate your prior beliefs and you get a much more narrow interval. All right, let me go ahead and give you your second view quiz answer for today. Today's second view quiz answer is the letter D. D as in dog. D as in dog. Second view quiz answer is D. Or data, or I don't know, some other D word. All right, we already talked about conjugate priors. And again, the idea of a conjugate prior is that the posterior distribution ends up being in the same family as that prior distribution. The prior distribution and the likelihood have mathematically nice properties so that they combine together in such a way that they combine nicely, and the resulting distribution, that posterior distribution, ends up having the same, belongs to the same family as the prior distribution. The beta and binomial are conjugate priors. You've got a bunch of other ones kind of listed off in Wikipedia here. So let's talk about getting our posterior distribution and then using that information to make some predictions. So let's go back to our baseball example. We said our prior distribution, we had alpha equaled 81, beta equal to 219. The new player has 10 at-bats, gets 5 hits. So he gets 5 hits, 5 outs. So after we go through the process, the updated posterior distribution, we're basically going to add 5 to 81, we get 86. We add the 5 outs to 219, and we get 224. And so let's say we ask this question. So this is our posterior distribution. And we ask this question. If this player has 3 at-bats in the next game, what's the probability he gets exactly 2 hits? What's the probability we get 2 hits out of 3 at-bats? All right. This question is like a stats 10 question, right? It's just, you learn the binomial probability, you plug in, okay, you just say, well, what's the probability he gets a hit for 1, and then you just plug that in and you get the thing, right? So, this is the question that this is the equation we would use. We would use 3 choose 2, theta to the second power, 1 minus theta to the first power. That's the probability of getting 2 hits out of 3 at-bats if the probability of getting a hit at any one moment is theta. Okay. Now, in Bayesian stats, this question gets a lot harder because theta we don't know the value of theta. Theta is a random variable. That makes it a lot harder, right? We can't just plug in one number and get the answer. I mean, we can, and we have a few choices, okay? So I've listed off 4 strategies that we can do for dealing with the fact that we don't know what theta is, okay? One is we can use a single value. We can just say, all right, we've got our posterior distribution. Let's use the mean of the posterior distribution and plug it in here, okay? Someone says, oh, no. We've got the posterior distribution. Let's use the mode and plug it in, okay? All right? We can also say, well, you know what? We've got the posterior distribution. We can find this value analytically. We're going to have to do an integral. It's going to be a little bit of work, but we can do it, okay? And then the last method that we will look is we're going to find the expected value via Monte Carlo methods, right? And this is going to be kind of our introduction to this concept of Monte Carlo estimation, okay? And what I hope to show is that, well, the analytic method is the most accurate, and the Monte Carlo is the easiest way to get something very close to the most accurate answer. Okay, well, I don't know. All right, so plugging in a single value, it's easy, okay? All we do is we're gonna say, hey, what's the mean? What's the mean of my posterior distribution, okay? Well, alpha is 86, beta is 224. The formula for the mean of this beta distribution is gonna be alpha over alpha plus beta. 86 divided by 86 plus 224, so 86 divided by 310, and we get 0.2774. That's the mean. And so we can say, all right, let's plug this in. 3 choose 2, 0.2774 to the second power, 1 minus 0.2774 to the first power. We get 0.1668, okay? And that's simple. You just take one value, you plug it in, and you say, this is my answer. Right? We're using the mean. Someone says, don't use the mean, use the mode, okay? All right, well, the mode is a little bit different, okay? Rather than 0.2774, which is the mean, we have 0.275974, so like 0.276, a little bit of a different number. So you plug in that number, 3 choose 2, 0.276 to the second, 1 minus 0.2, and you get a slightly different number, 0.1654. Here we got 0.1668. Here we got 0.1654. We're not making dramatic differences, but this is kind of the easy approach, right? This is, you just have a number, you plug it in, you get your answer. All right, the next slide, this one's the monster. Oh wait, no, not this one. This one's the monster, okay? Here, we're going to basically apply the law of the unconscious statistician. Basically, we're going to say, let's calculate the expected value of some function applied to a random variable, right? So we have the function g applied to the random variable x, right? The function here is 3 choose 2, theta to the second power, 1 minus theta to the first power, okay? And our random variable in our case is theta, and it's got this probability distribution. Right, so, to figure this out, we're going to take the integral across all possible values of that random variable. So we're going to go the integral. So it's the expected value of g of theta, and it's the integral from 0 to 1 of 3 choose 2 times theta to the second power, 1 minus theta to the first power, times the PDF of theta. Okay? And this is how we would calculate what's the expected value of the function applied to the random variable. Okay, so analytically, to get the answer, this is what we got to do. Okay, so it looks messy. It is a little bit messy, but it's also definitely doable. And and we could have put something like this in your homework, but I didn't do it. Okay, it's just I'm giving you the answer here. You already have a hard enough problem. You got the normal model one. That one's tough. Okay, so that's your one analytic problem in the homework. This one is done for you in lecture here. Okay, so we're going to just take this. 3 choose 2 is 3, okay? And then we pull out the constants, 3 and 1 over beta 86, 224. We combine the terms. And then so what's left, theta squared, 1 minus theta to the 1, theta to the 86 minus 1, 1 minus theta to the 224 minus 1. This we combine to theta 88 minus 1, 1 minus theta to the 225 minus 1. This will integrate to beta 88 225. And basically, using kind of the identities or what the beta function is, gamma 86 to gamma 224, gamma 86 plus 224 over here. Here I got gamma 88, gamma 225, gamma 88 plus 225. So now I have gamma 310, gamma 88, gamma 225, gamma 313, gamma 86, gamma 224. So we can think of these all as just kind of factorials. This is 309 factorial, this is 87 factorial, this is 224 factorial. This down here, gamma 313 is 312 factorial, gamma 86 is 85 factorial, gamma 224 is 223 factorial. And so there's a whole bunch of kind of canceling out of terms. And you get this, 3 times 1 over 310, 311, 312, 87, 86, 224. You multiply that out, and this is the analytic answer, 0.16715, right? All to say, this was a lot of work to get a number that's similar to just plugging in one individual value. But, we're getting something a little bit different, right? 0.16715. This one would probably be the most accurate as far as the expected value goes, okay? All right, and so the last method, so again, we can just plug in single values. We can approach it analytically, which was possible in this case, not always. And then the last one is we can approach it via Monte Carlo, right? So we went through this process and we were able to do it. Okay, it took a little bit of work here, but we were able to do it. And sometimes, though, you're in a situation where, well, maybe you just couldn't figure this out, okay? Or maybe you say, well, and this is often what happens to me, I go, that looks like a lot of work, okay? And so when you feel that way, a lot of times you can just take a Monte Carlo approach because you say, I don't need the exact answer. I just need something pretty close. And you get something really close, all right? So instead of having to do this, what we're going to say is rather than integrating across all of these values of x and some random variable x, what if we just did a whole bunch of these? We have a way to generate x from this PDF. Okay, we have a way to generate x from this PDF. Let's generate a whole bunch of these values. Let's plug those values into that function g, and then let's take the mean. And that's all we're doing, okay? So here, our posterior distribution is this beta distribution with alpha equal to 86 and beta equal to 224. How do we generate a whole bunch of values from a beta distribution? Okay, in R, we just use R beta. We just say, give me random beta values. Okay, so I'm going to say, all right, set seed 1. You don't have to set the seed, but it's often good practice. And we're going to say, I want 1 million values from the beta distribution. R can do this very quickly, right? I want 1 million values from the beta distribution, shape parameters 86, 224. This is going to be my sample. Okay, and then what is the function I'm using? G. G is a function of theta. And it's 3 choose 2, or 3 times theta squared times 1 minus theta. That's the function. So then what do? I take my sample, I plug it into G, and then I take the mean. And I get this answer, 0.1671577. How does that compare to the analytic approach? The analytic approach gave me 0.1671515. And we're accurate to 1, 2, 3, 4, 5 digits, 0.1671577. So we're very, very, very close, a little bit off, but this is closer. This Monte Carlo approach is closer than just using a single value, the mean or the mode. we're getting something quite close. And I think, well, I don't know, would you agree that this code is quite easy, right? Just give me a sample, plug that sample into your function, take the mean after you've applied the function to your sample. And that's it. And that's basically Monte Carlo methods, okay? We could end the, no, we were not going to end the lecture here, or I mean end the course here. But this is basically what you're doing. You're going to have kind of your first, you do this, I think, one time in your homework, okay? You just generate a sample, right? We've got R beta. We can generate values from, say, R beta. We can generate values from the gamma. There's a lot of distributions that we can generate values from in R. And we can do this, okay? So, you know, when we do the Monte Carlo method to kind of estimate it, it's pretty good estimate of the analytic problem, right? And a lot of times that analytic approach becomes too hard or just intractable. And so for these cases, the Monte Carlo method's estimate is very easy, right? And if I wanted to just switch it up, right? If I said, okay, instead of what's the probability of getting 2 hits out of 3 at-bats, what if we look at the next 10 at-bats and what's the probability he gets 4 hits? 4 hits out of the next 10 at-bats or something like that, okay? That's easy. All we have to do is we just change this. We would use the same sample, okay, or we could generate a new one, and I would just change this to whatever 4 hits out of 10 at-bats is, okay? Whereas taking the analytic approach, that's going to be a lot more work, right? So it's very easy to kind of just change things up. Just take a new, write a new function, plug it in, take the mean, okay? What we're going to start looking at in the coming weeks is we're going to kind of ask, well, you know, what do we do if we don't have a function like R beta? Okay, what if the posterior distribution has some weird shape that not described by the beta or some built-in function? Okay, what can we do there, right? Just all sorts of stuff. So this is kind of our first glimpse, and we'll keep building off of this. Okay, let me go ahead and give you your last view quiz answer. Last view quiz answer today is E. E as in elephant, or estimate, energy, whatever it is, okay? So there's your last view quiz answer. Okay, that's it. Have a good weekend, you guys. We'll see you guys on Monday, and that will be it. I hope your homework's going well.